Now let us take few more questions and answers in data structure and algorithm. So next is, what are the different ways of representing a graph? Represent the following graph using those ways. So this is a graph for you, and how we can represent this graph. So there are different ways of representing a graph. First is your adjacency list representation. How actually it is a list. And what about adjacency list? Because A is adjacent to B, so we have, if this is a list of A, then A is adjacent to B and B is adjacent to C, so we have C. C, now this C, how it is adjacent to E, we'll see. And because B is adjacent to C, so we write this, and then C has none, because there is no, because this is a directed graph, so there is no way you can reach from C anywhere. That is why we have null here also. And C null. Then D, let us come to D. D is with B, and then B is with C, this directed graph, and C is null. Again, E is B, and then B to D. Can you reach B to D? Is it possible? Okay, let us see. So this representation of graph consists of array, which is ADJ, adjacency list of V vertices, one for each vertex in V. So this graph has 1, 2, 3, 4, 5 vertices. So you can see 1, 2, 3, 4, 5. These are 5 box, as you can say. Okay, for each U V, the adjacency list ADJ is for adjacency U, contains all the vertices V, so that there is an edge E, that is ADJU consists of all the vertices adjacent to U in G. This is a graph G. So the vertices in each adjacency list is stored in an arbitrary order. These are arbitrary order. So the adjacency list representation of this graph can be represented like this. So I hope you got this adjacency list, and we have adjacency matrix. So these are two representation. Now this is a better form. Adjacency list is a better form because it does not waste the space, as we have seen, or as we will see in matrix. But our question was C to E, because there is no path from C to E, but we do not place the path. What we are doing is, because this representation, the adjacency list contains all the vertices V, such that there is an edge E, that is adjacent U consists of all the vertices adjacent to U. So in this case, A, B has a path, so we wrote AB. A, C has a path, we wrote AC. A, E has a path, so we wrote AE, right? So I hope you got this idea. Let us see one more, if any problem is there. We have D to B, okay, then we have D to C, so D to B is there, D to C is there, and E to B we have, and E to D also we have, so E to D, right? This is how we store adjacency list. Now we come to the adjacency matrix. So this representation consists of V by V matrix, that is ABCD row, ABCD E column. So 5 row, 5 column. And what is A is equal to Aij? What does it mean? Is if there is a path, there is a way from A to B. See whether it is there. A to B, yes, it is there. So what we are going to do here is, from A to B, we will place 1 here. From A to C, there is a path, we say 1. From A to D, there is no path, we say 0. From A to A, because this is a self loop, so we will write 0. And since A to E also has a path, means A to E you can reach. Can you reach A to E? Yes, you can reach A to E. So you take A to E. So these are the values 1, 1, 1. That means there is a path from A to B, from A to C, and A to E. So these are the path. And now I hope you understand how we are going to place this one. If there is a path, you place 1, otherwise 0. So you see there's a lot many zeros here. And these zeros are wasting our space. There is space. So how many space we need? This is 5 into 5, so 25. Where only 1, 2, 3, 4, 5, 6, 7, 8 edges are there, and we are wasting how many spaces? Okay, we are wasting around 17 spaces. That is why this is good. But sometimes you would require this to be there. We'll see various places where we would require it. I hope you understand there are two ways to represent the graph. One is adjacency matrix, another is adjacency list. Show the result of running BFS and DFS on this directed graph, given below using vertex 3 as a source. We'll start from here. and show the status of the data structure used at each stage. So depth first search, this will be like this. 1 is 8, then 1, 2. So we'll make a adjacency list first. 1, 8, 1, 2, then 1, 7, and then nothing, so none. So this you can make. Let me tell you one more, then I hope that you will understand this. Let us take 6 also. So 6, 5, so 6, 5 is there. Then 6 to 4, 6, 4 is there. Any other? No. There are only 2 outways from 6, so we'll have this. So this is depth first search, right? Now the other is depth first search. We start from vertex 3 as source and traversing above this. We are just in the adjacency list one by one. We get the result as 372865541. 372865541. 372868541. 86541. So first is our 3. In depth first search, we'll go to 7 first. 7 first. Then we go to 2. Then we go to 8. Then 6. And now this 6 reaches us. 6 takes us to where? 6. We are at 6 now. 6 will take us to 4. We are taking the depth first search. 4 and then 2, because only this one is remaining, so we'll take 1. So 3728641. Okay. Now breadth first search will give what? 372865541, and these elements, these are inserted from rear and deleted from front. Rear and deleted from front. So before removal of an element we insert, because we know that Q is used here, insert its element into Q. So the result of BFS in the graph we have just seen will be 372865541. Okay. Write an algorithm for finding solutions of Tower of Hanoi problem. Explain the working of your algorithm with 4 disks with diagram. So this is how we solve the Tower of Hanoi. These are n. This is initial. This is temporary. This is final. These are initial 3 variables. We have n numbers of disks, say with 4 disks. So if n equal to 1, we say move disk 1 from peg this to peg this. That is initial to final, and we return. Otherwise, we call Hanoi again. So this is a recursive solution. Hanoi for n-1. This is n for n-1, initial, final, and temp. And we print that move disk from initial to final. Again, we call Hanoi n-1 temp for temporary, initial, and final. So these are 3 calls, basically 2 calls, and inside this is the function. So there will be Hanoi calling this Hanoi calling again the function. So these 2 will be calling this again. And if n equal to 1, finally we move disk 1 from initial to final. So let us see. If we have say n equal to 4 and A, B, C, A is our initial, then we have B as temp, and final, this is C, that is final. So first A to B, then A to C, then B to C, and A to B. A to B, sorry. Then C to A, C to B, then A to B, and A to C. Again B to C, B to A, C to A, B to C, then A to B, A to C, and B to C. So there will be 15 moves. As you see, these are 15 moves. Reverse the order of elements on a stack S using 2 additional stacks, using 1 additional queue. How you can reverse the order of stacks, elements in a stack? First we see that we have to use 2 additional stacks. So let S be the stack having an element, and we need to reverse this element of S. So we use 2 stacks. This is S1, this is S2. So what we do here, we pop S, push it onto S1. We call push S1. Then while not empty, we put, or we take out from S1 and we push this C onto S2, the next one. And then we pop S3, C, and push SC. This is using 1 additional queue. what we are doing here is, while not empty, we are popping S, C, and enqueuing it in a queue, and then we are dequeuing and again pushing it into S. So I hope that I would encourage you to make a stack first, like this. If you have 3 stacks, S, S1, S2. So what you are going to do here is, you are popping S, so you are popping the highermost, say some X, and you are pushing it into S1, say X. Then what you are doing is, you are popping from S1, that is, you are popping S1, and then you are pushing into X2, X. Then you are popping from S3, and you are pushing into S. So every time you do it, every time you take it out, place this, so every time you reach here, you will be getting the value in reverse. So you are reversing the order of the elements. In this similar fashion, in this queue, what you are doing is, you have say a stack in which you have elements, and you are using a queue. So you are popping a value from here, that is a topmost value. You are enqueuing it into the queue, and you are dequeuing the value. After this all is done, means you have placed all values here one by one, one by one. And once you have placed it, you are dequeuing the value, means you are reversing it. How you are reversing it? Because you are taking this first, then this second, then third. So this is the order of reversing. Explain the representations of graph. Represent the given graph using any 2 methods. So as we have seen already that we have 2 ways. First is your adjacency matrix, or you can say adjacency list. The other one can be any of these. So you have two ways to represent a graph: adjacency list and adjacency matrix. They both have their advantages and disadvantages. Let me tell you again, we have taken a question like this, but we'll repeat it just to increase our knowledge again. So this representation of graph consists of an array ADJ of V lists. This is V list. How many V are there? 5. 1, 2, 3, 4, 5. One for each vertex V, 5 vertices. So 5 list. These are list. 1 list, 2 list, 3 list, 4 list, 5 list. So for each vertex, for each U in V, say 1 or any other, it consists of all the vertices adjacent to U in G. All these are adjacent because this is not a directed graph. This is undirected graph. Not directed graph. This is undirected graph. Previous one was directed graph. So the vertices in each adjacency list are stored in an arbitrary order. So the adjacency list representation will be shown like this. Let me take one of this. 1. So 1 is connected to 2. 1 is connected to 2. 1 is connected to 5. Let us take first 3 1. 1 is connected to 3. So 1 is connected to 3. And 1 is connected to 5. So 1 is 5. This is a list. Let us take one more. 5th one. 5th is connected to only 1. No other. So we take 5 1 and then null. Okay. This is how you form an adjacency list. And how you are going to make the adjacency matrix. You know that the representation consists of V by V. V into V matrix. That is 5 rows, 5 columns. 5 into 5. 25 cells. That is 5 rows, 5 columns. We have a matrix Aij. What is Aij? If it is 1, that means you have a path from 1 to 2. And 0, that is you don't have a path from 1 to 4. You can verify it. So this is how it is made. 1 is only placed when you have path from 1 to 3. 0 is placed if you don't have a path from 3 to say 5. Write notes on B tree, time complexity, B-word notation, merge sort, threaded binary tree, and depth first traversal. Let us learn them one by one. First of all, B tree. What is this B tree? Is it binary or balanced tree? So unlike binary tree, each node of B tree may have a variable number of keys and children. Variable number. So the keys are stored in non-decreasing order. They are stored in non-decreasing order. Means, can you say increasing order? Each key has an associated child, that is the root of the subtree, containing all nodes with keys less than or equal to the key but greater than the preceding key. A node also has an additional rightmost child, that is the root of the subtree containing all keys which are greater than any keys in the node. Greater, less. So B tree has a minimum number of allowable children. How many children are allowed in each node, which is known as the minimization factor. Minimization factor, not minimization factor. So if T is this minimization factor, every node must have at least T minus 1 keys. So under certain circumstances, the root node is allowed to violate this property by having fewer than T minus 1 keys. Every node may have at most 2T minus 1 keys or equivalent to 2T or 2T minus 1, where T is the minimization factor. And for n which is equal, greater than or equal to 1, the height of n key B tree, T of height h, is greater than or equal to 2. Okay, this is log, h log, and this is n plus 1 by 2. Log, which is basis of log because this is a balanced tree, right? We come to time complexity, big O notation. Don't worry about B tree, we are going to revisit it again with an example. Time complexity, big O notation. Worst case time or any other, the amount of time needed by an algorithm to run to its completion is referred as time complexity. Time needed by an algorithm to run to its completion. The asymptotic running time of an algorithm is defined in these terms of function. Asymptotic means the bound, lower bound or upper bound. Big O is the upper bound. So the upper bound of a function f is provided by big O notation, big O notation. If we consider g to be a function from the non-negative integers to be positive real numbers, we define this order of g as the set of function f such that for some real constant c greater than 0 and some non-negative integers constant and 0, fn is it greater than or equal to or less than. This fn will be, because what we are talking about is we have an asymptotic upper bound for our function gn. So fn will be, this gn is the upper bound of our function fn. So fn will always be less than or equal to cgn. And mathematically we can write our gn is fn if there exists a positive constant, say n0, for fn which is always less than equal to cgn for all n which is n greater than 0. So we say that f is big O of g. Then we come to merge sort. So merge sort is an efficient searching algorithm that uses the idea or technique of divide and conquer. This algorithm divides the array into two halves and sort them separately and then merges them. So this is recursive, means this will also be divided into 2. This will always be divided into 2, and this criteria will go on when we reach to number 1, means only one number is left and only one element is always, it is always sorted. So suppose variable low and high represents the index of the first and last element of an array respectively. The merge sort can be defined recursively like this. If low is less than high, when we divide the list into two halves, we merge the left half, apply merge sort in the left half, apply the merge sort in the right half, and this is not merge sort. We merge this is the actual, crux of, or you can say the heart of this merge sort, merging the two sorted halves into one sorted list. So this is only doing the, partition, but actual merging is the merge sorting, which is done by this. The merge sort gives you a very good complexity, big O of n log n. Then we come to threaded binary tree. What is this threaded binary tree? If a node in a binary tree is not having left or right child, or it is a left leaf node, then that absence of child node is represented by the null pointer. What we present it with the null pointer. So the space occupied by these null entries can be utilized to store some kind of valuable information also. So one possible way to utilize this space, which is held by the null pointers, is to have special pointers that point to nodes higher in the tree, that is ancestors, so pointing upwards. So these special pointers, these are called as threads. And the binary tree having such pointers is termed as threaded binary tree. So there are many ways to thread a binary tree. Each of these way either correspond in order or pre-order traversal of T. So a threaded binary tree is a binary tree in which every node that does not have a say right child has a thread. In actual sense, it is a link actually to the ancestor to its in-order successor. So thread will have a link to the in-order successor. And by doing this threading, we avoid the recursive method of traversing a tree, which makes use of stacks. Actually, it makes use of stack, which is very efficient and consumes which is not very efficient, and it consumes a lot of memory and time. So why to use this? Let us have things inside your tree only. So in this, the node structure of a threaded binary tree, it varies a bit, and it's like the node structure would be something like this. For a node, this will be a node in the form of structure. You have a left child, and in this you have a node value also. Then you have a right child, and then you have a thread, struct node thread. And let's make the threaded binary tree out of, say, normal binary tree. If this is a normal binary tree, the in-order traversal of this tree will be what? D, D, V, then A, E, C. Okay. I hope by now you are aware of what is the in-order traversal. Then this is D, B, A, E, C. So how we are going to brand or make this binary tree into threaded binary tree? What we are going to do is, B has no right child. It has no right child, and its in-order successor is what? A. So a thread has been made in between them. Similar with D. D also has no right subchild, so it will be pointing to B, or the thread will be pointing to B. In this similar case, this one also, E has no, so it will be like similarly for D and E. But C has no right child, but it has no in-order successor also. Do we have any in-order successor? B has in-order successor, A has in-order successor, E, C has no in-order successor. So it has a hanging say thread. It will have a hanging thread, not pointing to any link. So this is how it is done. Now we come to depth first traversal. Depth first traversal. So a depth first traversal of a tree visits a node and then recursively visits the subtrees of that node. A depth first tree traversal, it's like a traversal what we did in a tree also. So a depth first tree traversal of a tree, well, we are talking about tree now here, because depth first traversal is for graphs. So depth first traversal of a tree visits a node and then recursively visits the subtrees of that node. Similarly, the depth first search of a graph, we are talking about graph, visits a vertex and then recursively visits all the vertices adjacent to that node. So you can apply a depth first traversal for graph also and tree also, because tree is essentially a graph only. The catch is that the graph may contain cycles, but the traversal must visit every vertex at most once. And what is the solution? The solution to the problem is to keep track of the nodes that have been visited, so that the traversal does not suffer the fate of infinite recursion. Now we come to the other question. Define the term array. Define the term array. How a two-dimensional array represented in a memory? 2D array represented in memory. Explain how an element is calculated in a 2D array. So let us see what all this is about. An array is a way to reference a series of memory locations using the same name. These memory is contiguous. So each memory location is represented by an array element only. An array element is similar to one variable, except it is identified by an index value. So you can consider the size of array, number of variables which are kept in a contiguous fashion, and they are represented or known by only one name. And an index value is a number used to identify an array element, and these values should be homogeneous, means of same data type. How to declare a 2D array? A 2D array is declared in a similar way we declare a one-dimensional array, except that we specify the number of elements in both dimensions, like this is row, this is column. So in grades, for example, this is row, this is column. And for single array, what we can do? Say int age, say 10, like this. So this first bracket tells the compiler that we are declaring 3 pointers, each pointing to an array. So there will be 3 array of size 4. Okay, each pointing to an array. So we are not talking about a pointer variable or a pointer array. Instead, we are saying that each member of the first dimension of a two-dimensional array refers to a corresponding second dimension. So in this example, all the arrays pointed by the first index are of the same size. The second index can be of variable size. For example, in the previous statement, we declare two-dimensional array where there are 3 elements in the first dimension and 4 elements in the second dimension. Okay, so this is let me represent it here. It is like this. Say we have 3 rows, 1, 2, 1, 2, 3 rows. So there are 3 rows and 4 columns. 4 columns. So what we are saying is there are 3. We have 3 pointers which are pointing to these rows, and each row will contain 4 elements. So you can assume it to be 3 different rows in memory, and each row will have 4 columns. 4 columns. Okay. So the two-dimensional array is represented in memory in 2 forms: row measure and representation and column measure. And to represent this linear representation in a row measure, the first row of the array is stored in the first memory location. Means the first row will be taken and it will be placed in the memory. And then the second row, that means this row, then the third row, So this is how it is done. In column measure, what we do, first we take this column and we place. Then we say take the second column, place it here. Then the third column, not the row but the column. So here all the elements of the column are stored next to one another. In a row measure representation, the address is calculated in a two-dimensional array like this. Address Aij will be the base A. You need to know the base A first. Then I into M. This is I into M plus J into the size, because the size of the data type you are taking. Where this base A is the address of A00, M is the second dimension of array A, and I and J represent what? Size is the size of this data type. Now we come to another question. An array A contains n unique integers from range x to y. An array A contains n unique integers from range x to y, and x and y are inclusive where n equal to y minus x. N equal to y minus x. So that is, there is one member that is not in A, n is equal to y minus x. We have to design an order of n time algorithm for finding that number. How you are going to design it? Can you make it? Please try. An array A contains n unique integers from x to y, and we also given that n equal to y minus x. That is, y and x are inclusive. So this is the algorithm for finding the number that is not in array, where n contains unique n. So what we are going to do is, we are starting from, say, some I missing number Sn is the array. Okay, we are taking a for loop, I equal to 0, I less than n, I plus plus. So we assign Si as a very heavy number, means large number, and we start from all these values. Si is minus 1999, minus 999, minus 999. We start from 0 to n, and we see that whether Sai minus x, this Ai minus x is equal to Ai, right? Then we'll use this for loop. So I equal to 0, I less than n, I plus plus. If Si equal to minus 999, then the missing number will be nothing but I plus x, we break. This is the algorithm of order n. So these are a few questions again of data structure algorithm. We'll be taking more of these. Till then, thank you so much. Take care.